Feeling thirsty for knowledge? Hackers on the Rocks is the podcast that mixes refreshing conversation with potent cybersecurity insights. Serving up these insights with a twist, we pair a different software vulnerability with a refreshing cocktail recipe each episode. All right, hello world and greetings all around. Our opening segment is called Get Handle Information, and here to bring you today's drink, our guest, Robel Campbell. Robel, thanks for taking time out of your day to talk to us about cybersecurity research. Tell us, what are we drinking?
Hey, Evan, thank you for the opportunity. Today we're drinking a Blue Moon. I have mine poured right here.
Yeah, I'm about to crack one open. This is a favorite. You're not the first researcher to go with a Belgian style beer. What about this particular brand calls to you?
I'm not too heavy into drinks or anything like that. I had a Blue Moon once, and it was smooth and it tasted good, and I think it's fitting for how frequently I drink, which is once in a Blue Moon. So I think that's a good fit for me.
Oh, witty. I like it. All right. Well, cheers to you. And while we're drinking, I guess tell us a little about who you are and how you got into the research community.
So my background kind of begins in the Army. I kind of got my first start about 10 and a half years ago in the reserves. I kind of got my security clearance and like a beginner level IT cert. That kind of springboarded my career into just general IT. And then from there, I kind of locked down like what I wanted to do in that realm, and that was cybersecurity. Eventually, going to offensive security and reverse engineering. So I did the whole certification route. I got like a butt ton of offensive security certifications, and just really like honed in and got on my grind and studied hard, and that's kind of where I'm at today.
Yeah, I appreciate it. Before we get started on the next segment, I want to give special thanks to our sponsor, Dave Itel and Cordyceps Systems, for making this episode possible. That dude is making me read this word for word, reminding the world that neither of us does marketing. Cordyceps Systems, specialized AI and data processing solutions for specialized customers. Thank you, Dave, and the Cordyceps team. All right, our next segment is called The Distillery. Robel, what are we talking about today, man?
We're talking about shell coding.
All right, so a little bit different from other episodes where we tend to talk about bug classes. So I guess let's set the stage, right? So we've exploited something. There's been some kind of code injection, some execution. Like we own a system. What is shell coding, or what is shell code?
Shell code is just simply computer instructions. Uh, at its core, it's just a series of bytes that it basically just executes commands on a computer. So generally, like you have an exploit. Once you've gained control of the execution of that program, so you've exploited it, you gain control of the control flow of that program. You want to jump to your own code, and essentially, shell coding is just your own customized code to execute commands on that system.
So is this malware then? Is that what we're talking about? Like moving files, adding users, logging keystrokes, that kind of stuff?
Absolutely. Shellcode is generally just kind of like your initial the initial steps to executing code on a system. So it's not really fully robust with all these capabilities and features. It's usually just gaining what's called a command shell or some sort of connection to that machine. Now, it's not limited to remote connections or binding connections. You can also execute shellcode locally if you're trying to elevate privileges or anything like that.
All right. So if I'm understanding correctly, then the idea of shellcode is I've just gained execution and I have like this small space of stuff to navigate with. And so I want a small, tightly crafted program. And that program, to your point, like you said, there's either a shell instance or some like upload and execute, download and execute type functionality. And then from there, we kind of expand. Is that kind of how it works?
Yeah, pretty much. So the term shell coding, I believe it gets its name from getting a command shell. And so it's not limited to getting a shell. It's really whatever it is that whatever commands you want to execute on that system, be it like downloading something or modifying a file or something like that. You can pretty much the sky's the limit with whatever commands or things that you want to do on that system. But generally speaking, shell code gets you that initial command line shell to the system.
So if attackers are breaking on and they're generally doing, if I hear correctly, like one of three things, right? They're either like a shell is being kicked back to the attacker, or a shell is being staged in like a bind mode where the attacker will call in, or the shellcode does nothing more than like fetch other things to then install. That seems like a really narrow use of the target computer. Isn't this easy to detect then and to stop and prohibit, or like what makes this so challenging?
So there are various methods of detecting shellcode or basically figuring out like what the shellcode is doing. And you have kind of two separate things. You have built-in compiler protections on the program, and then you have like what endpoint detection and response and antivirus does to kind of detect malicious shellcode. And we can dive deeper into both of those if you like, or
Yeah, that'd be
kind of
great.
talk about.
Let's check the first. Let's talk about program protections.
Yeah, so some of the program protections to guard against shellcode are things like data execution prevention. So in your standard vanilla buffer overflow, you're taking control of the stack or the stack pointer. And so maybe you overflow the stack and you overwrite a return pointer, and it's going to return into your shellcode. Well, there's something called data execution prevention, which marks the whole stack as non-executable. So you have to resort to a different technique to get your code execution. Another mitigation is something like control flow integrity or control flow guard for Windows. And that basically blocks indirect calls to basically it takes a whole list of approved functions and puts it in what's called a bitmap. Just think of it as like a list of approved function calls that are allowed to call into other portions of the program. So if you overwrite one of those pointers and you're trying to jump to your shellcode, there's a check involved and it says, hey, like this is not an approved pointer, and then it shuts the program down. So those are two big ones on the compiler side. Um, then you have endpoint detection and response mitigations, and some of those features to kind of block execution of shellcode. And usually what those do is it hooks different uh, Windows APIs or Linux APIs. We'll just stick to Windows for now. So there's like API hooking where it looks for specific API calls that are necessary or used within the shellcode, and it kind of blocks that execution. It analyzes like what might be contained in the payload, or like where it's trying to write to, that kind of stuff. So there's a little bit of like fine grained control, or maybe even like machine learning on top of certain behaviors that they've implemented in that program or in the EDR to kind of detect on what the shellcode is doing or how it's being allocated and injected into something else.
So is
We
it
can dive deeper in.
yeah, is it then fair to say that an attacker needs to, I guess, custom build shellcode for every target then? It sounds like they're really trying to figure out, getting around, the debt prevention or some of the,
Yeah,
protections. And then now if you've got EDR, that's also looking at approved system calls. Sounds pretty complicated.
it can be. Now, so there's another uh, there's another prevention that's kind of built into the operating system itself, or even in the compiler, called address space layout randomization, or ASLR. Th There's various techniques that you can employ to bypass data execution prevention, ASLR, control flow integrity, and these are documented in various blog posts online. But um, so, for example, to get around data execution prevention, a lot of attackers will use what's called a ROP chain, or return-oriented programming, which basically reuses code within that same executable, like the vulnerable binary, to accomplish your objective. So instead of injecting your own code, you're just reusing the same code that's already in that program. Another thing to bypass, say, ASLR, is to get, say, like a memory leak. Um, I'll just talk about ASLR just in a general sense, but basically there's a randomization of memory addresses in that program, and it makes it difficult to predict where you are in memory in that program to craft your exploit. It just makes it really hard. So what you need is some sort of memory leak to kind of get a layout of the memory, like where you are, and like that helps you craft your payload when you're exploiting the program. So again, if you want to bypass that, you need some sort of leak or understanding of where you are in memory when you execute that. And then lastly, I'll just briefly touch on control flow integrity. Um, Usually to bypass that feature, you would need some sort of data only attack.
Mm.
And what that is you would basically overwrite critical structures or global variables or something that would enable you to uh, like elevate privileges or just kind of modify the nature of that program to either gain access or again like elevate your privileges. So it kind of takes some knowledge of knowing like what are some features in this program that I can manipulate just by modifying the actual data instead of injecting my own code and trying to execute arbitrary code.
So would you say then shellcode is maybe less dependent on the target in terms of operating system and architecture and more dependent upon the software that was used to initially gain execution?
The architecture is very much a key player in shellcode. You need to have matching architectures in order for it to execute. So, you know, if it's 64-bit, if this is a 64-bit operating system, you can either use 32 or 64-bit shellcode, and it has to be specific to that um, vendor, I guess. Like so, if like Intel, for example, you can't run like ARM architecture shellcode on on an Intel based system, that kind of thing. So you definitely have to factor that in. Um, you also want to account for maybe calling conventions, which is probably less important, but
What is a calling convention?
calling conventions are just how functions are executed and basically how variables are cleaned up on the stack, how stack space is allocated, and just basically how the APIs are executed for that operating system or that architecture.
Gotcha. So then it sounds like there's a lot, right? It sounds like we have to know a lot about the target software, the again, we said the processor of the machine running the software. Would
Right.
so shell coding then is more specialized than, I guess, your run of the mill malware, which I guess at that point uses abstraction layers and can just call things in the middle, right? So is that kind of the way you think of it? Or
Yeah, it's so typically shellcode is written in assembly code or assembly language. And it's also what's called position independent. And so one of the key features of shellcode is you have to resolve well, at least for Windows, you have to resolve the functions that you're calling. Meaning, one, you have to find where you are located in memory so you can execute wherever you are in memory. And then you also have to resolve the API calls that you're going to make to carry out the functionality that you're targeting. So there's various methods for that for obfuscating your you can have like a built-in encoding scheme that kind of, I guess, is like they call it API hashing, where basically you can implement an algorithm that looks up specific function calls, and you're just kind of living off the environment of the executable to kind of resolve the modules, the loaded modules, and their exported functions.
all right, so then there's a little bit of tolerance then, it sounds like, where if the shell code is executing and it doesn't have all the answers, it's possible to build some smarts to try and figure out where you are so that you don't result in some kind of a crash. Is that fair?
Yes, yes, it's very important that you have some sort of fail safe, I guess, if you will, just to make sure that uh, that you can execute anywhere flawlessly. And there's a lot of generators out there that are very robust. You probably heard of the Metasploit framework or even Cobalt Strike. There's various other frameworks out there that can help generate shellcode in a repeatable manner that will help kind of remove that complexity.
Yeah, again, maybe that's the piece where I think I'm still stuck, right? So if I can go to, Metasploit framework or Cobalt Strike user forum and just grab shellcode from somewhere, right? Maybe I don't even know what it is or what it does or how it works. That's isn't that static code? Like, couldn't we just write signatures and just say, if this is present in memory, don't run it? From an EDR perspective?
Yeah, yeah, you could, and that's a lot of what these, vendors do is they do have static signatures for these, more well-known frameworks. So if you just take, the stock shellcode that's generated, inject it into the program as your payload, I would say more often than not, you will get detected. And so there are built-in encoding schemes or decoding schemes, encryption, various ways to kind of hide the shellcode and the way it decodes itself that are built into these systems. But a lot of them are already, have some sort of signature or machine learning that's gonna pick it up. So it's helpful to kind of write your own shellcode if you can.
Yeah, and I know that a little bit of, like, backstory. I think that's part of the reason why I found you for this episode. Can we maybe talk about what it means to encode shellcode and, how one would do it and how it's smart enough to decode without the EDR decoding it as well?
Yeah, absolutely. Basically, you have like what's called a stub, a decoding stub, and that's like the beginning of the shell code, and it's actual real code that makes sense. If you decompile it, you look at it and it's like, okay, this legit. But then there's like this huge block of code after it that kind of looks weird. Like if you put it in a disassembler and you're looking at the code, you're like, these instructions don't make any sense. Well, that's actually the real shell code that's going to be executed. And so you have what's called a decoding stub that finds itself in memory, and then it basically implements some sort of algorithm, whether that's XOR decoding or some sort of decryption scheme that will just kind of iterate through the bytes in that shellcode and decode itself, and then it'll jump to the beginning of execution for that shellcode. And that just kind of helps throw off any sort of built-in signatures for the functionality of the shellcode. But I think vendors are making signatures for the actual decoding stub. So you kinda wanna it's like a cat and mouse, you kinda wanna
Yeah.
mix that up a bit.
Yeah, I remember that, back in the day. I mean, that's, when malware started getting packed, I mean, it was the same concept. Now you're looking for packing headers and whatnot, so, I guess maybe, backing up a little bit, if the operating systems provide software developers with tools, right? You mentioned, DEP, you mentioned, ASLR, and you mentioned control flow. Are there reasons why those are not just always on for everything?
Oh, I mean, apart from just general knowledge of the features, I think maybe some engineers or developers aren't fully aware of those features and why they would need to implement them. There's also the fact that these features can cause issues. If you incorporate some of these, it might break the program. So it's worth developing the program, enabling it, and then testing it to figure out like, well, is this something that my code will operate with flawlessly, or is this going to cause an issue down the road? And so I'll talk about another mitigation that's kind of there's like a strong requirement for it. You need like a specific hardware. It's called is it's by Intel. It's called Control Enforcement Technology, I believe, or Intel CET. It's basically hardware based. You need a specific processor to actually implement this, and it's just kind of like an enhancement um, for control flow guard. And so it implements certain instructions into your program that otherwise wouldn't be there, and it's backed by the computer or the actual CPU. Well, that might work for a lot of different programs, but it might not work for some other programs. Just depending on the way it's and coded, or even better, you still need the specific hardware to get that feature or that functionality, and not everyone's going to have the capability to do so. Like it's one of those things that'll probably be rolled out more in the future, but like right now they can't benefit from that feature.
Got it. Maybe you can back up one final time for me. I'm still maybe hazy on, like, an attacker's methodology, right? So, attacker finds, to your point, some kind of, Stack Overflow and, knocks it over, has this buffer of space, places inside it, shellcode, and is able to then tell the CPU to like execute on those instructions. Um, I guess that part seems really complex and confusing, right? Because of all the things we've just said, right? There's just a lot of things that could go wrong if the systems have all these control flows, protections, or um, EDR type technology. And I guess even there, like just to get that code running sounds complicated. Like why you why do anything more? Why not just stick within shellcode? Why do you need like a follow-on tool?
So shellcode needs to be small enough to exploit that program. So shellcode is it depends on how large your buffer size is, if you will, or like how much space you can allocate within that program to place your shellcode. The smaller the better because it's like your initial crowbar. Like if you're trying to get into this system, like you just need something quick and easy to get in first, and then you just need a little bit of code to actually get your follow-on payload. And so rather than incorporating a large, robust, uh, let's just say like a Cobalt Strike beacon like, as your initial payload, that's going to be a very large amount of shellcode that you may not have enough space for. So you want to start off small with like an initial stager payload, and then use that to download or unpack your second stage. And it's just largely dependent on the program you're exploiting or how it's being exploited. Hopefully that answered the question.
Yeah, I think so. I mean, maybe last call, right? Anything I'm not asking you that I should? Like, is there anything that the audience should know about shell coding that we haven't covered?
um, I would just say that there are a lot of mitigations being developed for just general exploitation that are making it harder and harder to exploit systems, especially in Windows. If so, I'll talk a little bit about um, the the whole, I guess, how you reached out to me in the first place. The post that I made on LinkedIn. Um, that specific case was different in the sense that it was shellcode being used in the Windows kernel and not so much the user land space or just like a regular process. This was also post exploitation, meaning this wasn't like exploiting a certain like a program and gaining access first. This was actually like they've already had access to the system and they are injecting their own shellcode in the kernel. The reason why this one was kind of interesting was because leveraged uh, it leveraged physical memory addresses to write into the kernel, and typically, if you try to modify portions of the code in the kernel, you would get hit with something called kernel patch protection, which basically is like, hey, you're modifying portions of code in the kernel that are not supposed to change, specifically like the executable portions, and your system would crash, it would blue screen. But because this leveraged physical memory, those protections aren't as valid or they're not really checked. And so this isn't a new technique. This is something that is, if you have this sort of exploit primitive, it's very effective. But they use the physical memory addresses to map virtual memory, which is like the virtual memory of the kernel, to write their own shellcode, like overwriting another module's code. And so nothing happened. It just kind of like, there was no like alerts that going off, nothing blue screen, everything executed successfully, and they basically wrote their own rootkit in the kernel, which is pretty interesting. So again, it's like a cat and mouse game. That there's all these different bypasses and methods to kind of get around these things, but the protections are growing and getting better and better.
I appreciate that. I think one thing I'll commit to the audience since you mentioned it. I don't think we've done an episode yet on virtual memory and mappings and kernel space and IOCBLs and all that kind of jazz. So I will commit to the audience that we will have an episode on all that. That is absolutely its own episode.
Yeah,
Uh,
for sure.
it sounds really interesting so far. What you're saying, if I'm following, um, you have. I guess I mean it was your phrase. You actually went right there, right? So there's a kernel mode rootkit that is like slowly overwriting various syscalls and I don't know, that's a slick technique. I think we probably do an episode on that as well. Um, since you mentioned, LinkedIn, I guess, last call, like, where or can people find out more about you, your work, or anything you mentioned today?
Yeah, so I work for Blackpoint Cyber. I'm a principal security researcher over there. I do a mix of things. I'm You can find me on x.com at Robel Campbell. LinkedIn, you can just Google search my name in LinkedIn if you want to connect. I'm always happy to connect. And I also have my own side business. It's called Reverence Cyber. I do some subcontracted work, anything from reverse engineering malware, pen testing, vulnerability research. Just do a mix of things. And I'm also an instructor for Applied Technology Academy, teaching offensive security courses, specifically the Advanced Windows Exploitation course. Should be teaching that at this year at Black Hat.
Rock on. Busy man. Look, Robel, I really, really appreciate you taking the time out of your day to talk about shell coding. Appreciate the research, appreciate the insight. Thank you for your time.
Thank you for having me. I appreciate it.
Yeah, cheers.